Welcome. This is Unit 2, Lesson 2, and the topic today is going to be on the relativity of motion. We're going to start this out by talking about a specific scenario. So, pretend that you are waiting at a bus stop. So we have maybe just a little road here, right? And you're just kind of chilling at this bus stop. You're a happy little guy there. While you're at this bus stop, you notice a bus passing on the other side of the street. And on the bus, and I have limited artistic ability, obviously has some people in it. You make eye contact with a passenger in this bus, and you conclude a couple things. And here's our little friendly passenger. You conclude that this passenger is moving, right? And you assume this because you see the bus moving. You know that you are physically not moving. And yet, something that this guy could do is say something very similar. This person on the bus could very easily say that I'm not moving and you're the one who's moving. Because if you're on a bus and you're sitting down, that doesn't really seem like moving too much, right? So motion depends on your frame of reference. So that's a word we want to define, frame of reference. So why don't we write that out? A frame of reference basically represents your initial point. So your initial point to make measurements from. So I spelled that wrong. So your initial point to make measurements from. So the way, and we're going to go over this more later, the way that you measure if someone is moving is you measure their distance from a certain point. So for us, we're using our frame of reference. If I were to draw this picture again down here, we have us represented as this dot, and we have this bus where over time it moves. And relative to us, it is moving. Right? Our coordinate system, or our frame of reference, right, is all centered on this point. If we were to measure, for example, from our vertex to this point, and then our vertex to point 2, and our vertex to point 1, we would notice that our distance is decreasing. Right? As it gets closer to us, our distance decreases. The thing is, we can actually change this around. If you remember, if we're measuring in the frame of reference of the Earth, right, we know that this Earth, right, goes around, this is my quick drawing of the Earth, goes around the Sun, right, Sun in the distance here. Right, so we can't even really say that we're the ones who are standing still, because relative to the sun, we're actually moving quite fast, over 1,000 meters a second, which is, I believe, 2,000-ish miles per hour. But is our sun moving? It actually is, relative to a different reference point, to the center of the universe. The sun goes around, right, our galaxy. So if I were to zoom out, right, if this is the center of our galaxy right here, right, we have a nice little spiral galaxy. Right, we are, as a solar system, moving around that. And if we were to zoom out even further, I can't zoom out further on the screen. Our galaxy as a whole is moving really, really quickly in some random direction relative to all the other galaxies out there. And these just look kind of like eggs. And all of these are all moving in every which way. In our universe, we don't have a center point that we say that is the 0 point. That is the point where everyone measures from. And so that kind of can make things a little bit interesting, because going back again to this guy in the bus, as much as we can say based on us measuring his distance over time, which essentially is our speed, we can say that he's moving, but he can very well say that we're moving, because if he is his frame of reference, so if he is right here, this is his frame of reference, technically speaking, he is always the 0 point. So if we're always measuring from himself, he's always going to be at 0. So in his frame of reference, it actually looks like we are the ones who are moving this way. And again, if we measure to all these points, we see that our distances are decreasing. So we're getting closer, we're changing our distance over some time, we're moving at some certain speed. So a frame of reference is very important to define. And in physics, the best way we define it is first by choosing our starting point, and then choosing a direction as well. So, for example, if this person, again, we'll call him person A, probably should have denoted them in the beginning. Person A can't make the statement and say that person B is actually moving, but if he chooses his words carefully, he can. Person A can say that person B is moving in relative to person A's frame of reference, and person B can say the very same thing, that person A is moving relative to B's frame of reference. So this is going to be important. Another thing that kind of manifests from this is directions. So we're going to talk about this just very, very, very quickly. So let's look at this bus problem again, except let's just look at the bus itself. So we know, all right, here's my bus that looks like a box. There are passengers on this bus, and we're not really going to focus on the other passengers. We're just going to focus on one passenger. So let's just say this bus is moving at 20 miles an hour. And we have a person on this bus moving, or just kind of standing there, right? This 20 miles per hour is measured in a certain frame of reference, and this is relative to someone standing outside of the bus, right? Someone standing outside the bus would also say that this person right here is also moving 20 miles per hour. Question now becomes, what happens if this person begins to move? So let's say now that this person begins moving at 5 miles per hour in this direction. And we're going to note this as the positive direction. In physics, right, positive and negative aren't kind of like factors in the way that you think they are. Really, all positive is a direction. All negative is the opposite direction of positive. So directions, or signs, I guess, in physics are really just directions because they have real-world applications. So anyways, we do this, and we would say that this person is moving relative to our outside frame of reference at 25 miles per hour. And the way we get that is we have the bus moving this fast. And for the person to be moving further up towards the front of the bus, he would have to be moving faster than the bus. Right, so altogether, he's actually moving 25 miles per hour in our positive direction. So maybe we add a little plus sign there. Now, what if something opposite happens? So let's say he is now over on this side, and he wants to begin walking down this way. Let's say he's in a hurry for whatever reason, moving at 10 miles an hour. So now we know that the bus is moving 20 miles an hour, but this guy is moving at 10 miles an hour in the opposite direction. So this is a little confusing. If we added these together, and we would get technically 30 miles an hour, but we know that's not correct. He's not moving 10 miles per hour faster than the bus. He's actually moving backwards. So in our frame of reference, what we need to do with movement when it's in opposite directions is actually just subtract them. Since his direction is pointed in the direction opposite of positive, we would actually just call him moving in negative 10 miles per hour. So we throw a little negative in there. Now if we want to solve this, it's actually pretty easy. We get 10 miles per hour. So in our frame of reference outside of the bus, if we saw him moving at 10 miles per hour, we would see him moving back towards the back of the bus. But also let's keep in mind, to someone sitting on this bus, in their frame of reference, this person is actually just moving a negative 10 miles per hour, right? Because that 20 miles per hour of the bus isn't taken into consideration when our frame of reference is actually inside the bus. So this might sound a little bit confusing, but it'll start making more sense as time goes on. There's actually not too much math related to this. Pretty much all I want you to be able to do is set a reference point and choose your direction of what is positive, what is negative. So that's all I have for you today. If you have any questions, feel free to contact me. Email, discussion board, whatever it is. All right, have a good one.